Hello AP Stats students, welcome back. For this video, we are going to talk about Chapter 11, and Chapter 11 is all about the basics of significance tests. So this is really where we get into the formalities of the inference test, okay? So what we're going to do for this first section, section 11.1, is we are going to break this into two installments, okay? This is a lot of information, and I don't want to bog you down all at one time. So I've recorded two videos for section 1, okay? So for this first part, let's just go ahead and we'll introduce a significance test, okay? So a significance test, it's this formal procedure for comparing observed data with a claim, which we call a hypothesis, whose truth we want to assess, okay? So we know that someone has made a statement about a population, say for instance, like the mean GPA of all students that go to South High is a 4.0. And you know a couple people that don't have a 4.0, so you are doubting this claim. So what we're going to do is we're going to set up this set of hypotheses that are going to represent our suspicions, and then we're going to be able to carry out some procedures to then go ahead and test the claim, okay? So a significance test here, first of all, it always deals with a claim about a population. And a significance test asks if sample data give good evidence against a claim. Okay? And then also it says if we took many random samples and the claim were true, we would get a result like this. Now we're going to go back to chapter 10, our confidence level, or C percent, or our confidence level, C percent of the time, okay? And then also here, just the basic idea, an outcome that would rarely happen if a claim were true gives us good evidence that the claim is not true. And so this is the whole idea around this this big idea of statistics, is this concept of statistically significant or statistical significance. Okay, so basically, if something rarely happens by chance, that means that that's good evidence against this claim that someone makes. Okay, so if it's rarely happens that all students at a high school have a mean GPA of 4.0, then that gives us good evidence that claim is false. Okay, so let's look at this example. We're going to look at an example about someone who likes to shoot free throws here. It says a basketball player claims to make 80% of the free throws he attempts. You have seen him play basketball before, and you don't believe him. So you ask him to shoot some free throws in front of you, okay? Suppose he shot 50 free throws, and out of those 50 free throws, he makes only 32 of them, okay? Is his claim true, but he just had a bad streak, or is his claim false? So let's look at p hat. What is our sample statistic here? So p hat is going to be the number of successes, 32 out of the total 50, right? And what this gives us is 0.64, or 64%. So if someone says they're an 84% free throw shooter, but you see him just make 50 free throws and they only make 64%, is, is there good evidence there? Is there something to doubt here that things just aren't right? Okay? So what we have here is we have a graph that represents a sampling distribution of sorts. And what the details of this sampling distribution are, we have 400 simulations of shooting 50 shots here, okay? If in fact this person is a 80% free throw shooter. So we've made this person line up and shoot 50 free throws a total of 400 times. So then we look at this sampling distribution and it's centered at 80 because remember they are what they say they are. They're an 80% free throw shooter. So if it's true that in fact they're an 80% free throw shooter, then we would see them have a bad streak as bad as shooting 64% or worse. They could even shoot, maybe 62%. We have 1, 2, 3 out of the 400 times. 3 out of 400 times, which is equal to 0.0075. So that is less than 1% of the time they will actually have such a bad streak. So this probability is a number that we use in statistics to give us good evidence against a claim, okay? So what this means, what we're going to write up here is this idea of statistical significance. So if, in fact, the basketball player is an 80% free throw shooter, the probability they will have a free throw percentage of 64%, or lower by chance alone is 0.75%. And this part right here, by chance alone, that's really important. That's the whole idea of this idea of statistical significance is what's the probability something is just going to happen just by chance, okay? We don't do anything to influence it. It just happens. So if this person is an 80% free throw shooter, we will see them have this bad of a streak or worse only less than less than 1%, which is pretty low, okay? So moving on here then, what that means for us is that it says, what is the probability that he made 32 out of 50 shots just by chance alone? Well, we just found that. So based on the simulation, our estimates say that this probability is 0.0075. Okay? So since this number is so low, the observed statistic P hat is 64%, is so unlikely that it gives us convincing evidence that the player's claim is false. Okay, so we don't believe him. Now there's two scenarios here that could happen, okay? So I want you to be sure that you understand why the evidence is convincing. So our first possibility number 1 says, well, this player could be correct. They could be an 80% free throw shooter, and they just had very bad luck. But this is a very unlikely outcome, right? This will only happen, this bad luck will only happen less than 1% of the time, right? Or option number 2, the population proportion is actually less than 80%. So this free throw shooter is not an 80% free throw shooter, okay? So the sample result is not a unlikely outcome because this statement is false. The original statement is false, okay? Now we're going to go on and we're going to talk about how to set up some hypotheses here. Now, whenever we start an inference process, we always start with number 1, stating the parameter, and then stating our hypotheses. So that is step number 1. So when we state our hypotheses, I say hypotheses plural because there's going to be 2 of them. There's going to be the null and the alternative hypotheses. So the null hypothesis, or HO, so this is HO, the null hypothesis is a statement of no difference. So it basically means that the claim is true, all right? And the alternative, HA, is the claim that we hope or we suspect is true. And we're going to use the basketball example to set up some examples of some hypotheses here. Now, there's 2 types of alternative hypotheses. There's a one-sided alternative hypothesis, and there's a two-sided alternative hypothesis. Okay, so let's use the example of the free throw shooter. So what this free throw shooter is claiming, okay, is that they're an 80% free throw shooter. So P is equal to 0.8. Now the null is always going to be equal to whatever is claimed to be true, okay? And then the alternative can take on 3 different signs. It can either be greater than, less than, or not equal to, okay? So what we suspect after seeing him shoot his free throws is that he is a free throw shooter who makes less than 80% of the free throws. So what we suspect is that P is less than 0.8. And when we do a one-sided, what this means in terms of our normal curve here is it means that we're looking at this area down here. What's the probability that we're going to see an outcome as small or smaller than our observed outcome? The other side of that is, let's say hypothetically that this free throw shooter was actually like Steph Curry, okay? Now, if you know anything about basketball, Curry's a pretty darn good player, and maybe he's just kind of a modest and humble guy, and he's like, yeah, I'm an 80% free throw shooter. So our null is going to be P is 0.8. Now, if you know anything about basketball, you are going to doubt that claim because you know how good Curry is. So your alternative, what you suspect is true, is that he is actually better than that. So our alternative hypothesis is that P is greater than 0.8, okay? Now, the difference between this one and the last one is that now we're going to be looking at the upper tail, the right side of that tail, where what's the probability that Curry will shoot as many or more free throws in this sample. Now, an alternative hypothesis that's a two-sided hypothesis is a claim that the parameter is not equal to a specific value, okay? So using still this example of the free throw shooter example, we could say, our null is that P is equal to 0.8, but our alternative is, maybe I don't know if this free throw shooter is better than 80%. I don't know if they're worse than 80%. So I'm going to set my alternative to just not equal to 0.8. Now, you have to be careful with this because this is a mutually exclusive event. What this means essentially is the probability that P is greater than 0.8 or P is less than 0.8. And these are mutually exclusive. Yeah, I'm having trouble spelling that. Okay, so just to review, back in chapter 6, mutually exclusive events cannot happen at the same time. So you can't be, say, a 60% free throw shooter and a 90% free throw shooter. So what that means is we have to combine the areas. So on our normal curve, what that means is we are going to actually be looking at the probability that we will observe a sample statistic less than or at a given value or smaller, or at a given value or greater. And we're going to be combining those two tails together. Okay? So what we're going to do here is we're going to practice setting up some hypotheses. And I need to break for just a second. I'll be right back. Hang with me here. Okay, so my computer was about to die, but I got it plugged in here. So we're all set to go. So for example number 2, what we're going to do here is we are going to set up some hypotheses. And let's read example number 1 together. It says, Mike is an avid golfer who would like to improve his play. A friend suggests getting new clubs and lets Mike try out his 7-iron. Based on years of experience, Mike has established that the mean distance that balls travel when hit with his old 7-iron is 175 yards with a standard deviation of 15 yards. He is hoping that this new club will make his shots with the 7-iron more consistent. Okay, that particular statement right there, more consistent or less spread, is very important. And so what he does is he goes ahead and he takes this new 7-iron to the driving range and he hits 50 shots. Okay, so what we need to do is first we need to state our parameter, and then we're going to decide what sort of hypotheses we want to set up here. So we are talking about spread is standard deviation, right? So as our when we state our parameter, we're going to say let sigma here equal the true standard deviation of Mike's drive distances with his new 7-iron. Okay, now part B, we're going to set up the null and alternative hypotheses. So let's think about this. We want his drives to be more consistent or less spread. Okay, so we have to either say I want a one-sided, so I want it to be greater than or less than, or I want a two-sided, not equal to. So we are hoping, our hope is that his standard deviation is going to go down. He's going to have less spread, more consistency. So what we're assuming here then, we're going to assume standard deviation is going to decrease. And so this implies a one-sided alternative. So what we're going to do is we're going to assume for the null that his standard deviation is the same. So it's 15 as stated in the problem. Okay, so that's what we know. that's what is claimed to be true. And what we're testing is that his standard deviation has decreased. So it's less than 15. So since we're looking at less than, we are going to be looking at the left tail here. Okay? Let's go ahead and look at example 2. It says the school principal is not pleased with the first semester exam scores for 2 first period U.S. history classes. The mean test score for both classes was 72. He believes that the students' final exam score average will increase because the 2 teachers will teach the second semester by combining the classes and using a team teaching approach. Okay? So we're going to describe the parameter. We're talking about an average. That means mu, right? So we're going to say let mu equal the true mean final exam score. Score. Okay? So then for our hypotheses here for part B, okay, the assumption is that they will increase. So we're going to assume scores will increase. So that means we want a one-sided again. So our null is what we know to be true, okay? We know that the average is 72. And what we're testing is to see if this team teaching approach will increase the scores. So will it bring that average to a number greater than 72, okay? So when we look at this curve, when we go to do our actual significance test, we're going to be testing the right tail there, okay? Now let's look at 3. It says the human body is designed to maintain a very balanced pH level of its fluids. The normal pH of blood is about 7.4. When the body's blood is not at normal range, things start to go awry. Blood that is too acidic, or when the pH is too low, or too alkaline, which means the pH is too high, can cause dangerous conditions that weaken all the body's systems. A patient presents with weakening systems. The patient has been experiencing weakening symptoms for almost a year, and each time the symptoms are present, the patient goes to the clinic. The nurse automatically checks the blood's pH level, okay? So it says, so each time these symptoms present, the patient's going to go to the clinic, okay? So essentially, we're going to gather this data and we're going to want to take an average of these pH levels. So we're going to let mu equal the true mean pH of the blood for this patient. Okay? So the deal here is that weakening symptoms present when the pH is off. And the pH is off when it's not 7.4. Okay? So our assumption here, we're going to assume pH is not 7.4 because this patient has these weakening symptoms. Okay? So the pH could be too low, it could be too high, and all of those would cause weakening symptoms. So we're going to use a two-sided alternative. So HO, then we're going to assume what is true. We're going to assume that the mean pH is normal level, 7.4. But our alternative, what is causing these weakening symptoms? Well, maybe the pH is off. Maybe it's too low or too high, or in other words, it is not 7.4. So on our bell curve here, what we're going to be looking at is the probability it's too high, the probability it's too low together, okay? Now, we've got, I think, one more example problem here. Oops. To focus on setting up these alternatives before we wrap up the first installment of this video for section 1. So let's read it together. It says, a VitaBlend, a new brand of vitamins, claims in a radio advertisement that people who take VitaBlend vitamins wake refreshed and ready for the new day within 5 minutes of their alarm sounding. VitaBlend's internal research department wants to test this claim. Okay? How great would that be to be able to take a little vitamin and you wake refreshed and ready for your day within 5 minutes of your alarm sounding? Well, if you're anything like me, the worst part about my entire day is getting out of bed. So that would be like a magic pill in a sense. So what we're going to do here is we're going to define our parameter. We're going to say, let mu equal the true mean time it takes to wake refreshed and ready for a new day after taking VitaBlend. So the true mean time it takes to wake refreshed after consuming VitaBlend. Okay, so let's see here. They want to test this claim. Is it in fact true that people will wake? Uh-oh. Well, my dogs seem to have sounded the barking alarm. I'm sure they'll calm down here in just a second. Okay, here we go. Okay, so what we're going to do is, Brenya, Farron, come here. So what we're going to do is we're going to, sorry about that, we're going to we want to test this claim, right? That they wake within 5 minutes of consuming the VitaBlend vitamins. Okay, so if that claim is false, okay, let's assume let's assume the complement. If it's false, then they would wake in more than 5 minutes, right? So what we're going to assume here is then that it takes them longer. Our assumption is that it takes them longer to wake up. Okay, so our null is going to be mu is equal to 5. That's the original claim. That's what we know to be true. In our alternative is that, what we're assuming is that it takes them longer than 5 minutes to wake refreshed. So mu is greater than 5, okay? So this one would be a right tail. Now, this is kind of an interesting example because it can be kind of confusing to decide which way do we want this tail to go, okay, to test this claim. So what we're going to do is we're going to kind of wrap this up by looking at a few pointers here when we set up our hypotheses. So the first point is the alternative hypotheses should express the hopes or suspicions we have before we see the data. Okay, so we don't, it's kind of considered cheating if we look at the data before we actually set up our alternative. Okay, so for example, if someone says they're an 80% free throw shooter, we need to make a claim about them before we see them actually shoot the free throws. We can't see them, only make 32 out of 50 and go, yeah, I don't think you're really an 80% free throw shooter. Okay, so the alternative has to come before we actually see the data. The second point is the hypotheses always refer to the population parameter and not the statistic. Okay, so on that note, what I do not want to see is I do not want to see, like, say for instance, HO is X bar is equal to 5. Okay, that's using a statistic. Or I do not want to see HO P hat is equal to, say, 0.5. Okay, that's a statistic. We want to use parameters. So instead, we want to say, whoops, not alternative. I want to use the null. Instead, I want to say mu is equal to 5, or I want to say P is equal to 0.5. Okay? And then the last bit here kind of references this last example. If you are unsure if it's a one-sided or a two-sided, it's best to use a two-sided. And that's because it's going to give you a larger p-value, and we're going to get into the nitty-gritties of all these details in a little bit later on. But if we have a larger p-value, we're less likely to reject when we shouldn't be rejecting. Okay, so it's better to err on the safe side, and if you're confused, do a two-sided hypothesis. Okay, so this wraps up the first installment of 11.1. There's another video to follow that will take us through the remainder of section 11.1. So what I want you to do is take a little brain break, maybe 5 minutes, maybe a little bit longer than that, just kind of refresh some of those neurons in your brain, and then get ready to carry on with the second installment of 11.1. Okay, see you soon.